Okay. Hello, everyone. Who are there? Hi, Puvik. How are you? Yeah, Puvik. We'll discuss some question. We'll discuss some past year JE question, and again, since it is a revision class, so a little bit of concept also we'll discuss. Okay. So basically, we are trying to cover the whole chapter today in 3 hours. Okay. So every every single thing we'll not discuss in this session. But again, what all session or the section are important in this chapter for JE point of view, and few questions based on those concept we'll see. Okay, so yeah, so basically, since it is already end of September, we have then October, November, December, January. You have JE main exam, correct? And we are almost about to finish the syllabus. Okay, in coming few days. Okay, so after that, we have to revise the whole thing of 11th and 12th chapter in by the end of November. Okay, so this is just we are starting this thing from today. Okay, so hello everyone. Hello, Sai Mehir, Purvik, Ritvik, Kushal, Sanjana, Shweta, Shruti. Okay, so since you have finished this particular chapter in 11th class, okay, so will I you must have the uh, idea of this, the basic idea you already have. Okay, so you can text me because I'll go a bit fast since we have to finish this chapter today itself. Okay, so you can text me wherever you will have problem or difficulty. Okay, so initially we'll start with all those basics things, the terms that we use in this chapter. Okay, and then we'll go a bit faster, right? So first of all, you see thermodynamics in this chapter will deal with flow of heat, right? How the heat dynamics means what? Dynamics means motion, thermo means heat, right? So basically in this chapter we'll deal with flow of heat, right? How the heat flows and work done, internal energy, and all those things we'll discuss in this chapter. Okay, dynamics means motion, correct? So before going into this particular chapter, first of all we have to understand certain terms into it, and those terms are the first term. I'm straightforward. I'm going into the chapter, that is system, and second one we have, that is surroundings. Okay, system is anything which is under consideration. Okay, and you don't have to write. See, I will usually, like when I take classes, I usually dictate all those theories and concepts, so that you can make your notes properly. Okay, so in this class I am not going to dictate all those things because again we don't have that much time. Okay, so I'll just write down every possible thing here, and I'll uh, say every possible thing. Whatever you feel important, you just write it down on your notes. Okay, or you feel like, okay, this point you have to keep in mind, or suppose you have forgot those points, so you can write those points. Okay, so system and surroundings. System is what? System is anything which is under consideration, right? System is anything which is under consideration. Suppose if I take one pen or marker or a notebook or anything, and we are talking about that particular pen, anything, if the pen is at this height or that height, in terms of energy, if you're talking, or anything, suppose if you're talking about any object, right? So that object at that point of time becomes system for us, right? And every other thing is surroundings, right? Suppose in the classroom I'm talking about the whiteboard. Okay, so this whiteboard is the system, and every other thing in the class is surroundings, right? So system plus surroundings gives you universe. Okay, so universe are made up of system and surrounding. Okay, so in this chapter we mainly deals with system. Okay, see, one more thing you can understand here, which is very basic, you must know. But then also I'll tell you one more time this thing, that whatever change you do in the system, okay, whatever change you do in the system, if you work on the system, or if system is doing work, then there will be change in the energy of the system. Either the energy of the system will increase or it will decrease. Correct? With respect to that change, the change in surrounding is negligible. Okay, what is the meaning of this? You try to understand. Suppose the system is releasing some energy, right? Suppose the system is at the system is at suppose 300 Kelvin, right? And suppose it does some work and its temperature decreases of the system to 300 to 250 Kelvin or 290 Kelvin, suppose, right? So this is the change in temperature of the system we have. What happens? Whatever the energy or heat this system releases, that heat is obviously taken by the surroundings, right? Yeah. So whatever heat releases by the system and its temperature decreases to 290 Kelvin, this 10 Kelvin, which is the difference in temperature, it is given to the surroundings, right? So if I ask you what is the decrease in temperature of the system is 10 Kelvin, right? And this 10 Kelvin of or whatever the heat releases in this process that is taken up by the surrounding is very large, right? So suppose you have a pen, right? You are in the classroom and you have a pen, right? If this pen releases some energy, so this energy goes into the entire classroom, right? So since the size of surrounding is like is comparatively big in comparison to the size of the system that you have, that's why the change in surrounding, change means what in terms of energy or whatever you say, right? The change in system with respect to that, the change in surrounding is always negligible. Okay, this idea also helps you sometime in solving the question. The very no the basic example of this you can understand. If you have in the classroom or wherever you are in the computer lab or wherever it is, right? If you switch on the AC, the temperature of the lab decreases, right? Whatever temperature you fix over there, according to that, that will be the temperature of the entire classroom or lab, right? But the heat of the classroom is going outside, right? Going into the surroundings, right? So within the classroom, you will have less temperature, right? But outside the classroom, the temperature, the change in temperature is not that much. Okay, you will not feel any decrease in temperature in the surroundings when you come out of the classroom, right? So this is a very basic example we have, that change in system we can observe easily, but with respect to that, if you try to observe the change in surroundings, it is negligible. Okay, always, right? So this one thing you must keep in mind. Now you see, since we are talking about system, right? So system are mainly classified into three categories, and you know all these things, so I won't take much time on this. But why I am discussing this, because on this you may have multiple choice question in JEE exam. Okay, that's why I'm discussing this. So definition, I hope you all know. If not, then you can tell me. I'll tell you what is the definition we have. And the system we have three types, that is isolated system, open system, and closed system. I hope you know the definition of all these three types of system. Correct? What is isolated system? Isolated system is what? There is no exchange of mass and energy, right? Suppose if I take a system like this, if this system is isolated, right? So neither exchange of mass or nor exchange of energy is possible in this. Okay, so energy and mass exchange with surrounding is not possible in this if the system is isolated, right? So there is no exchange of energy and mass we have in this, right? So what we can write, in isolated system, the energy is constant and the mass of the system is also constant. Okay, similarly, what is an open system? Open system is this. Now, since it is open, so exchange of energy and mass both possible, right? System is open, so exchange of energy and mass both possible. So in this, the energy is not constant and mass is also not constant. Nothing is constant into this. Okay. Yeah. What is closed system? Closed system is what? Exchange of only energy is possible. There is no exchange of mass. Energy possible, energy exchange is possible, but mass exchange is not possible. So what happens in this? Mass is constant, but energy is not constant. This is what the definition we have. Correct? Now you see, on the basis of this definition, you may have multiple choice question that they have asked already in very previous exam. Okay, 90s. Okay, I'll give you 5, 6, 4, 5 statement. Okay, I'll just rub this off. I'll give you 4, 5 statement, and this is the true false statement, right? Just you have to give me the answer whether it is true or false, right? Like this, they can give you 4 option in multiple choice question. Okay, so you have to be very clear with the concept. See, let me tell you one thing in this chapter I have seen many times most of the students they attempt question from this chapter, but mm, most of the students I have seen they have ended up with the wrong response with the negative marks, because in this chapter you may have numerical question also, you may have conceptual question also, theoretical question. Okay, so you have to be very clear with the concept, right? So first of all, you see the first statement that I am giving you is a closed statement always has constant volume. What I said, a closed system. Let me write down the statement first, all those 4, 5 statements. Then you give me the answer. Okay, and you also write it down. This one you also write it down. Okay, a closed system always have constant volume. The first statement is this. Second one, neither heat nor matter is exchanged, then the system the system must be isolated. System must be isolated. Isolated system will be a closed system. Next one, an adiabatic container an adiabatic container fitted with rigid adiabatic piston will be will be an example of closed system. Will be an example of closed system. Okay, now you tell me the true, which of one of these statements are true or false. One more, if I give you, a closed must be system must be an isolated system. A closed system must be an isolated system. Okay, think on all these statements once and give me the answer, true and false. Okay, Pratik is saying second one is true. Shweta 1 and 2 are true. Shweta is saying 1 and 2 are true. Shruti 5 is false. What about other Shruti? Kushal, true, true, false, true, false. 3 is true because being a closed system is a prerequisite to be an isolated system. 3 isolated system will be a closed system. Sanjana is 5 is false. Purvik, true, 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 false, false. Pratik, how will third one be false? What about the fourth one? What about the fourth one? An adiabatic container fitted with rigid adiabatic piston will be an example of closed system. Okay, now you see. The first question we have, a closed system always have constant volume, right? A closed system always has constant volume. You see, this statement is false, right? Why? Because you see, if the system is piston cylinder system we are taking, and this piston is movable piston we have, right? You see, the system is closed, but since the piston is movable, it can go up and come down also. So the volume is not constant, right? Okay. So the first one is false. The second one, neither heat nor matter is exchanged, then the system must be isolated. Is it true or false? Neither heat nor matter is exchanged, then the system must be. This is also false. You know why? Because we can do the work onto this. Okay. See, the isolated system means what? There's no exchange of heat or energy or matter, right? But the exchange of energy takes place in the form of work also, right? We can exchange energy while when we do work also on the system. If you're doing work on the system, or if the system is doing work, in that form also the exchange of energy is possible, right? So since there is no exchange of heat or matter, but because of work done, the exchange of energy is possible into this. That's why the second statement is also false, right? Isolated system will be a closed system, right? This one is true, right? Isolated system will be a closed system, right? System, if it is isolated, so it must be closed, right? So it is correct. Now the fourth one you see, sorry, it is true, no? Third one is true, right? Fourth one you see, an adiabatic container fitted with rigid adiabatic piston will be an example of closed system. Is it a closed system? It is an isolated system, right? So this statement is also false, right? Since it is closed, right? The piston is rigid, so we cannot move this piston up and down, right? Piston is rigid, it is adiabatic also. This system is also adiabatic. So since it is adiabatic, no exchange of energy possible into this, right? So this is the definition of what? Isolated system, right? That's why this statement is false. If it is isolated, it should be closed. See, isolated means what? No exchange of energy. What I told you here, system is closed, but if the piston is movable, then exchange of energy possible, right? Isolated system. See, this is the one of the condition we have, right? See, the closed system, we have two types of closed system. One is what? When the piston is rigid, constant volume closed system. And when the piston is movable, where the volume is not constant, right? So when we are saying that isolated system will be a closed system, it is correct, right? But when you are saying adiabatic container fitted with a rigid adiabatic expansion, here you see, we are talking about a closed system here. Try to understand this, okay? System is closed means the piston may be fixed, may be movable. Both conditions are satisfied here. But with fixed piston, this statement is false, right? But if you consider what? If you consider movable piston, then this statement is true, right? So since it is only mentioned about the closed system, so we'll take it as true, because for isolated, the system must be closed, right? Now, if here you see in the next statement, an adiabatic container fitted with rigid adiabatic expansion, rigid adiabatic piston will be an example of closed system, right? So this will be a closed system, right? But the thing here is what? That the piston is movable, right? If it is movable, then the energy exchange is possible. Then it will definitely be a closed system, correct? If you see the definition of isolated system, you will get this as the definition of isolated system. So if I write here isolated system, then this statement will be correct, right? Now the last one, you see, a closed system must be an isolated system. This is also false, right? Closed system with movable piston, it is not an isolated system, correct? So like this, on the basis of this open system and closed system, you can have this kind of question in the exam, okay? Multiple choice also or single choice also, you can have this kind of question, okay? So you must keep this particular thing in mind, okay? Now you see, this is the one type of question that forms in the exam. Another one is what? That is related with thermodynamic property, okay? Okay, but before that, we'll see one small thing here, since we are dealing with this uh, various terms that we have. State variable, okay? State variables are those term actually we have, which depends on state only, right? Example, you see, example, we have temperature, we have pressure, we have volume. All these are state variable, right? It depends on only the state of the system, right? Suppose here the temperature is, suppose here the energy, or suppose here the temperature is 300 Kelvin, right? And here the temperature is suppose 100 Kelvin we have. So no matter how do we come to this point, whether this path or this path or this path, but whenever you are at this point, the temperature must be 100 Kelvin. Whenever you are at this point, the temperature must be 300 Kelvin, right? So all these are what? All these are state variable. It depends on the state of the system, at what state the system is, right? Now the important thing here, and this thing that we are going to discuss here, that is thermodynamic property. On this they have asked question in JE exam, that I'll give you after the discussion of this particular topic, okay? Thermodynamic properties. Okay, so thermodynamic properties, you see, uh, thermodynamic properties are of two types basically. Okay, and those properties are what? Extensive property and intensive property. Extensive and intensive. What is extensive property? Anyone? Extensive property depends upon the amount of substance. Okay, so extensive properties are what? It depends upon the amount of substance or upon mass. Okay, or mass. Okay, whatever amount you are taking, it depends on that. Extensive means independent. Intensive, independent, right? Independent of mass, right? On the basis of this one question they have asked previously, that question I'll give you. But there are some examples we have for extensive property that you write down first, and you must keep this in mind. Okay, you will definitely have this question. Okay, whatever exam you'll write, whether you write JE, whether you write BitSat, whether you write Karnataka CET or NEET also, right? So you will definitely have one question on this. It is possible, right? You see, depends upon mass, right? So whatever this heat capacity, suppose if I write down the mass itself is an extensive property. Volume also depends on mass. If you take 1 ml of water, that will have a definite value of mass. 100 ml of water will definitely have different mass, right? So mass, volume, moles, okay, all these energy term, in short I'll write down Gibbs free energy, enthalpy, entropy, internal energy, right? Heat capacity, heat capacity. All these are mass dependent term. That's why if you try to recall, since you have done this chapter earlier, when we do thermochemistry and whenever we define enthalpy of formation, okay, enthalpy of formation, there always we use the term 1 mole. It is the energy required to form 1 mole of substance, right? What is the enthalpy of combustion? It is the enthalpy of neutralization. It is the energy required or releases or required when 1 mole of acid get neutralized by the base, right? So we always, uh, defines the amount that we are taking. Since all these terms are what? All these terms are extensive properties, depends upon the mass, right? So these are the example of uh, extensive property we have. Intensive property, you see, all terms which are all concentration term are intensive property, all concentration term. Like in example, molarity, molality, all those are intensive property. Okay, concentration does not depend on mass. Okay, concentration term are intensive property. Density is also intensive property, right? Density, you see, density will write mass by volume, right? But this is actually intensive property, because when you suppose water you have, whether you take 1 glass of water or 1 bucket of water, right, the density of water will not change, correct? So density is always an intensive property. If you change the mass, in proportion to that only volume also changes, so that m by v ratio will be maintained. We can understand this mathematically also. Suppose we have a container and the mass of this container is suppose 2m and the volume is 2v, correct? So initially the density is what? M by V, mass by volume. 2m by 2v, 2 will get cancelled. Now when you divide this vessel into two equal half, then the mass of this part will be m, volume will be v. Mass of this part will be m, volume will be v. So whatever the density of this part, d is equals to again mass by volume, m by v. So you see, whether you take 2m mass, the density is m by v, or you take m mass, the density is again m by v. Okay. Okay. Yeah. Again, since mass and volume both are extensive property, the ratio of two extensive property gives you intensive property. That also you can write down. Correct, Simon here. Okay. So when you take the ratio of two extensive property, you will get an intensive property. That also you can keep in mind. Okay. So concentration term, density we have, temperature, pressure, temperature, pressure, mole fraction, molar enthalpy, molar enthalpy, molar entropy, molar entropy, refractive index, or you can write down specific heat, viscosity, surface tension, dielectric constant, electric constant, pH, or EMF of the cell. All these are intensive properties, pH and EMF of the cell. Now you see, on the basis of this, one question that they've asked in previous year, and that question is, the question is identify the intensive quantities from the following. Okay, JE 1993. Okay, JE 1993, intensive quantity you have to find out: enthalpy, volume, temperature, and refractive index. Okay, enthalpy, volume, temperature, and refractive index. Okay, so this was actually the multiple choice question, multiple correct answer we have. So first option they have given what? Enthalpy. You have to find out intensive property. Enthalpy they have given first option, then they have given temperature, then they have given volume, and then they have given refractive index. So you see, enthalpy is what? Enthalpy is the extensive property, not possible. Temperature is an intensive property. Volume is also an extensive property. Refractive index is an intensive property. So answer will be B and D in this. Okay. Which one of these are intensive property? Simon here. Enthalpy, temperature, volume, refractive index. Okay. Done. Temperature, yeah, temperature and refractive index are the intensive property. Okay. Now you see, there are various. See, I am assuming that you already know this first law of thermodynamics and all that. We are not going to discuss. Okay. So only few things we'll discuss about that. That I'll tell you first. Okay, and then we'll continue with this. Okay. So first of all, we'll discuss work, right? So we'll discuss work first, and then we'll go into this. Okay, there are a few, what I say, conversion in this we have important. Okay, so work, you see, whenever we say work generally in thermodynamics, we are talking about pressure volume work done. Okay, pressure volume work done. Okay, there is a convention, sign convention we have into this. Okay, and that is work done by the system. Okay, work done by the system is always negative. Work done on the system is always positive. Okay, whenever system does work, okay, then expansion takes place. These few things you must remember. Okay, when we do work on the system, then compression takes place, volume decreases. Okay, now whatever the process we have, okay, you must have got various expression of work done in various different processes. Okay, but the only formula of, or the basic formula of work done we have, right, and that will be W is equals to W is equals to minus P external into dV, where this volume can change from Vi to Vf, initial to final volume. Okay, this is the only formula of work done we have. Now whatever process we are taking, right, according to that we'll apply the condition and we'll get the formula of work done. Okay, you must have done in physics that the work done by the system is positive and work done on the system is negative. Yes or no? Tell me this one. In physics, you must have done work done by the system positive and work done on the system negative. Yes, but in chemistry, it is opposite. Okay, work done by the system is negative and work done on the system is positive. Right? Because you see, in physics, generally we take external pressure. Suppose you have a piston cylinder system like this. Okay, in physics, generally we take this pressure, external pressure. But in chemistry, we'll take pressure, the pressure of gas, internal pressure that we have. This is the pressure of gas and this is the external pressure, right? So suppose it is just a convention, right? Suppose you are taking pressure in this direction positive, so obviously the pressure in this direction is what? Negative, right? Negative. And that's why we have written minus P external into dV here. Minus P external means what? P gas is equals to minus of P external. Okay, so this one thing you don't get confused with. Okay, in chemistry we always take work done by the system negative and work done on the system positive, right? Now can you tell me, this is very important. Okay, now can you tell me what is the unit of work done we get from this formula? What is the unit of work done? See, from this, the unit of work done that you get, that will be what? The unit of pressure and the unit of volume. And that will be what? From this formula, whenever you calculate from this formula, you always get unit of work done in ATM liter. Pressure is ATM, volume is liter, right? No, Ritvik, no, Ritvik, that's what I'm telling you. Purvik, no. Saimi, no. Because you see, we have pressure and volume, right? So we always get from the formula, we'll get Pascal meter cube. Fine. Fine, we'll get ATM later, or in terms of Pascal also you can say. Correct? So this is the unit we have. So but in the option you will not get this ATM liter. You will get unit in terms of joule, right? So ATM liter, this conversion you must keep in mind. Okay, 1 ATM liter you have to convert in joule, then you have to equate this with 101,325 joule, right? Or if the pressure is in bar, then 1 bar per liter is equals to 100 joule you have to substitute. Okay, so this you must keep in mind, this conversion here. Okay, usually whatever value you get here, suppose you are getting 100 ATM liter, so they'll give you 100 joule also in the option. In hurry we generally take, okay, we got 100, so it will be 100 joule. Okay, so don't make mistake over here. Unit conversion is also important. Okay, now if one or two condition we'll take here. If we have closed and rigid system, right? Closed rigid container, suppose if we have. What do you mean by closed and rigid container? Means its dV is zero. There's no change in volume because the piston is rigid now, right? When dV is zero, then work done will be what? Work done will be zero, right? So in this case, work done will be zero. Or if you have P external zero, then also work done will be zero, right? Okay. Now you see the next term that we have, that is internal energy. Okay, you tell me one thing. Just one thing I wanted to ask you. Change in internal energy du is equals to ncv dt is one of the formula we have. Yes or no? When can we use this formula? When can we use this formula? Du is equals to ncv dt. Constant volume. Okay, I know that you all give me this answer only. Where is Purvik? What is the answer, Purvik? Vaishnavi, Shweta, what is the, oh, you have given volume is constant. Pratik, Kushal, Vaishnavi, what is the answer? Okay. So you see, all of you are saying constant volume, but this is not true. Okay. This formula we can use for all process. For all process, whether the volume is constant or not. Okay. We can use everywhere this formula. Why? You try to understand this. Okay. So internal energy, you see, internal energy basically, we'll start with the basic thing from this. Okay. Internal energy, I don't know, Purvi, what are you saying? Anyways, we'll discuss this. See, internal energy is what? It is the summation of, or the sum of all kind of energy, right? Kinetic energy, potential energy, and chemical energy also. And chemical energy also. Means whatever different kind of energy, whatever energy you have, everything you add for the system, you will get the internal energy of the system, right? Chemical energy means what? It is the energy which involves in bond making, bond breaking. Energy involves in the nucleus also. Everything comes into this. Okay. Kinetic energy is what? Kinetic energy is nothing but the, because of the motion of the particles, right? And motion can be translational, rotational, and linear also, translational, rotational, and what we have, the next one, vibrational also, right? All these three kind of motion includes kinetic energy. Potential energy is what? It is because of the position, right? Because the position of the molecules of the system. All these kind of energy, if you know add, then you will get internal energy of the system. Practically, if you see, it is very difficult to calculate all these energy and add those to get the absolute value of internal energy, right? That's why we do not ever calculate absolute value of internal energy, but we actually calculate the change in internal energy, del U. We always calculate del U, the change in internal energy at one position and another position. We never calculate the value of U. You also must have observed, if not, then you can go through some of the question. They never ask you what is the value of internal energy. They never ask you this question. They always ask you what is the change in internal energy. Because the absolute value, to calculate the absolute value is very difficult into this. This is the one thing. The next thing is what? We all know that the kinetic energy is what? The kinetic energy is the function of temperature, right? Potential energy is the function of volume. Why volume? Because you see, the system molecules, if the volume is suppose large, right, then the system molecule will be away from each other. The distance between the molecule will be more when the volume is very high. But if the same amount of gas you put into a small volume, then the distance between the two molecules will decrease. When the distance will decrease, its potential energy will also change. Correct? That's why we say the kinetic energy is a function of what? Sorry, potential energy is a function of volume, and we neglect this chemical energy, right? Because the change in chemical energy is very minimal, okay, always. So we generally neglect this chemical energy. Now we have two different variables, and we can write down the internal energy is equals to the function of temperature and volume, right? Now if you know this Euler's formula, we can write down the change in internal energy du is equals to dou u by dou t at constant volume into dt plus dou u by dou v at constant temperature into dV. This formula, you know. Have you done this formula? This we call it as Euler's theorem, Euler's formula. Anyways, okay, Euler's formula. See, Euler's formula you can apply whenever the one variable depends on more than one variable like this. You see, U depends on TV, and suppose if I write down like this, no, suppose if you see Y is a function of suppose P, Q, R, right? Then what we can write, the change in Y is equals to dou Y by dou P, keeping this Q and R constant into dP plus the another term like this we write. Okay, so anyways, it is not that important. This we call it as Euler's formula or Euler's theorem. Euler's theorem. Okay, EULERS. Okay, Euler's formula or Euler's theorem. Okay, so anyways, you let it be. This is not at all required, but let me tell you one thing here. Now if you one thing, if you remember that the heat content, you must have done this derivation from here that I'm doing just now. Heat content at constant volume is equals to Q, which is nothing but U we have, right? And at constant pressure, Q is equals to H, that is enthalpy, right? Okay, internal energy is the heat content at constant volume, and enthalpy is the heat content at constant. Enthalpy is the heat content at constant pressure, right? So I did not, give you this thing initially, because it comes from the heat capacity, right? And what is the heat capacity? I'll just tell you here only. Okay, this term, you just let it be. Will come to this again. Heat capacity is what? It is defined by the heat required to change in temperature by 1 degree Celsius. Heat capacity is what? Heat capacity is C. Suppose if I write dq is the amount of heat required to change the temperature by dt. Okay, heat capacity is what? It is the amount of heat required to change the temperature by 1 degree Celsius, right? Amount of heat required. I'm repeating this again and again. If you do not have this, you write it down. Okay, heat capacity is what? It is the amount of heat required to change the temperature by 1 degree Celsius, right? So C, if I write down, dq is the amount of heat required to change temperature by dt. So for 1 degree Celsius change in temperature, the heat required is what? dq by dt, and which is nothing but C we have according to the definition, right? Now, when I take constant volume, right, it is the heat content at constant volume. So at constant volume, what we can write, this dq is equals to du, and at constant pressure, this dq is nothing but dh. Okay, we'll come to this dh part later on, but this is what at constant volume, dq is equals to du. So if I substitute here, you see, this is the heat capacity at constant volume if I write. So Cv is the heat capacity at constant volume, and this dq becomes du here. So du by dt for 1 mole we are talking about. Cv is equals to du by dt, and then what we say, that this du is equals to Cv dt. And for n moles, we'll write ncv dt. Yes or no? I think I guess you have done like this only, this derivation. Yeah, correct. Yeah, you see, if you do the derivation like this, okay, by the definition of heat capacity, you always get this only, and you will say, okay, we can use this formula whenever the volume is constant. But that is not true. This formula we use for all process. Now we are just taking the reference of this thing over here. Now you see, du by dt is what? Cv. So for n number of moles, this formula becomes du is equals to du by dt is Cv, that we can write for n number of moles, ncv dt plus du by dou u by dou v at constant temperature into dv. This is the actual formula of change in internal energy for all process. Whatever process we have, for all process you can use this. Okay, whether the volume is constant or not. Correct? Now you see one thing. If you see this term here, U, internal energy, right? This is what? Internal energy, right? This is internal energy. Du is the internal energy, right? I'll just make some space here. Okay. Now you understand, try to understand this term. du by dv. Du is the internal energy, right? And energy we can always write pressure into volume. Try to understand the unit of it. Okay. So you wrote dq as du because at constant volume q is equals to u, so you should not be at constant volume. No, actually you see this du by dt, right? In this expression we are coming from here, right? We are coming from here, right? So du by dt, here do we apply any condition here from this to this step? Do we apply any condition? We did not apply any condition over here. Just du by dt at constant volume we write Cv. This is the simple definition of heat capacity at constant volume. It is a definition of heat capacity at constant volume. We haven't applied this any condition over here. The definition of heat capacity, that's why I was paying attention over there, that definition of heat capacity. Heat capacity is the temperature, heat required to change the temperature at 1 by 1 degree Celsius at constant volume, right? The heat content is nothing but the internal energy of the system. It is the another definition of internal energy, right? At constant volume, the heat content of the system is nothing but the another internal energy of the system. It is for all process Q is not equal to U. If it is for all process, Q is not equal to U. Yeah, if it is for all process, Q is not equal to U. No, actually, you see, again, this from this to this term we are writing down, it is just a definition of internal energy. Okay, that's what I'm telling you. One way to define internal energy is this: all kind of energy you add. Internal energy is also the heat content of a system at constant volume, right? So this from this to this you are getting over here. It is by the definition of internal energy, right? Which is the heat content of the system at constant volume, right? So simply that is the definition of U we are taking over here. We are not applying any condition. We are not keeping the, see, whenever you have internal energy, U, correct, you will have some value of this, okay? Whether the volume is constant or not, right? So when you take the volume constant and you try to find out the internal energy of the system, then also you'll get the same value. That's why we are having this definition also, right? So when the volume is constant, then the heat capacity is defining by this Cv, and this is equals to du by dt at constant volume for 1 mole, right? That is the definition of heat capacity at constant volume, right? And that definition we are just using over here to write down one expression. That is it. We are not applying constant. If so, suppose if you take constant volume here, right? Constant volume, if you take, then this term automatically becomes zero, no? If you take constant volume. But that is not we are taking over here. We are just substituting the expression here. That is it. Okay. Now, one thing you see, dou u by dou v, by v we can write u is an energy, right? And pressure volume P into V is also an energy. So this we can substitute here. And this volume will get cancelled. We'll get the unit of pressure over here. Correct? So since this is the internal energy, so we call it as internal pressure. Try to keep this, the term in mind. Dou U by dou V is what? Dou U by dou V has the unit of pressure, and we call it as internal pressure. Okay. Now for ideal gas, now the general formula is this, which is applicable for all process. Now in this we are taking the condition, and the first condition is what? For ideal gas, because 99% of the situation we are dealing with ideal gas, right? And we know in ideal gas there is no intermolecular attraction. Gaseous molecules are not attracting, right? There is no intermolecular force, right? So since there is no intermolecular force of attraction, there is no internal pressure. A will be zero. A is the correction factor of pressure there we have in gaseous state. A will be zero. And that's why the internal pressure, which is dou u by dou v, is 0. And when this is 0, you substitute this here, you'll get the formula, which is dou u is equal, du is equals to ncv dt. So for ideal gas, the formula of change in internal energy we'll get is ncv dt for ideal gas. And that's why we use this formula directly. But for real gas, if they have given, they must give you at constant temperature the relation of internal energy and volume. That you have to find out this by the given condition, and then you have to add these two, you'll get the change in internal energy. Then I hope you understand this. See, we got this formula of change in internal energy is equals to this. This is the du is equals to, yeah, correct Purvi. Correct Purvi. This is actually for ideal gas, right? The actual formula of change in internal energy is this. We'll get from Euler's formula. Wait. I'm telling you. Let it be. This, let it be. Actual formula of change in internal energy is this, right? Now, in this, if you take the unit of this, U is the energy. So, energy we can write pressure into volume because that is the work done. Work done is nothing but energy. And volume gets cancelled, we'll get pressure. Means du by dv, dou u by dou v is nothing but the pressure unit we have. Since U is the internal energy, we are calling it as internal pressure. Okay. Now, in case of ideal gas, there is no internal pressure, right? In case of ideal gas, there is no internal pressure because the ideal gas molecules, we do not have any interaction into this. If you remember gaseous state, right? Since we do not have any interaction, so A value, which is the pressure correction factor, will be 0 in this case. And when A is 0, the internal pressure is 0. And when the internal pressure is 0, dou u by dou v is 0. When you substitute this dou u by dou v 0 over here, you'll get du is equals to ncv dt, right? So du can be ncv dt in two cases: when we have ideal gas or when we have constant volume. Constant volume means what? The vessel is rigid. Okay, if you have rigid container, closed rigid container, if you have, okay, closed rigid container, if you have, then only the change in volume is 0, which gives you du is equals to ncv dt. Understood? Yes or no? Okay. So we'll see some questions onto this after some time. Okay, one more thing we have to discuss here. So, like the bottom line of all this story is what? Du is equals to ncv dt. You can apply whether volume is constant or not. We don't have to do anything with volume thing over here. For ideal gas, for rigid container, we can always apply du is equals to ncv dt, whether the volume is constant or not. Okay. Now you see another thing here. So for 1 mole, we have just now we have done that du by dt is equals to Cv, right? Now, if you're talking about enthalpy, right? So heat capacity, write down this thing, heat capacity at constant pressure is Cp, right? And Cp we can define as, at constant pressure we can also write, or write down like this. Enthalpy is the heat content of the system at constant pressure. Okay, so dq is equals to dh when the pressure is constant. Okay, and again heat capacity is what? It is the amount of heat required to change the temperature by 1 degree Celsius. So suppose dt is the change in temperature we have when we supply dq amount of heat into it. 1 degree rise in temperature, the heat required is dq by dt. If it is constant pressure, so this will write dq by dt is equals to Cp. And we know at constant pressure dq is nothing but dh we have. So Cp we can write down dh by dt. Okay. Now we can also write down one more relation here, that is dh is equals to du plus pdv. Okay, at constant pressure. See what we can write. H is equals to u plus pv is the mathematical definition of enthalpy we have, right? H is equals to u plus pv. Or if I suppose if I write down q here, right, from first law of thermodynamics, right? So at constant pressure, if I write down dq is equals to what we can write? Du plus constant pressure we have, so pressure outside, dv we write. And we know at constant pressure dq is nothing but dh, so we'll get this expression, right? Now if I divide both sides by dt, so what we get? Dh by dt is equals to du by dt plus pdv by dt. So dh by dt is nothing but Cp, du by dt is nothing but Cv plus R. Pdv by dt is nothing but R we have, gas constant. Right? So we'll get the formula Cp minus Cv is equals to R. This is the derivation of this we have, which is important for board exam also. Cp minus Cv is equals to R. One more thing we have here, the ratio of Cp by Cv is equals to gamma, right? And if you combine these two, we'll get Cv is equals to R divided by gamma minus 1, and Cp is equals to gamma R by gamma minus 1. This is the formula of Cp and Cv we have in terms of gamma. Right? We have a formula in case of chemical reaction, and that is again important. If chemical reaction is given, then we write down del H is equals to del U. In terms of T del V, we'll write delta Ng RT. Okay, where this delta Ng is the delta Ng is the number of moles, or in short, if I write down moles of product, and the product we always take which are in gaseous state, minus moles of reactant. This also must be in gaseous state. Okay. Now, one thing you see from this expression, it is important. Okay. From this expression, if delta Ng is less than 0, which means what? This is nothing but the work done we have. This part is nothing but the work done, because you see, work done is what? Like I said, the formula of work done is always minus of integral PdV. Always the formula is this we have, where we have V initial and V final. Since we are talking about enthalpy on the left hand side, and we know it is the heat content of the system at constant pressure. Yeah. See, Shweta, what happens whenever we are talking about one thing, all of you must understand properly. Whenever this reaction, this formula is always true for chemical reaction. If chemical reaction is given, or suppose if chemical reaction is not given, they'll give you like this: what is the change in enthalpy we have when the combustion of methane takes place? Okay, so we know when methane combustion takes place, it forms CO2 and H2O, right, where CO2 is in gaseous form. So like this you will have the information of chemical reaction. The first thing is that this reaction or this formula we can always use when chemical reaction is given, or right? Now, any chemical reaction, if it is not mentioned, it always takes place at constant pressure and constant temperature process, right? Any chemical reaction, if it is not mentioned, it always takes place at constant pressure and constant temperature. So obviously this T is constant over here, right? Understood, Shweta? Okay. Now you see work done is this. So since the pressure is constant, so we can take this pressure outside, and when we solve this, we'll get what? Vf minus Vi, right? Now Vf, what we can write? Final volume. Can we write this as final number of moles for gas into RT? Final number of moles for gas into G stands for gas here, minus the initial number of moles for gaseous particle into RT. P will not be there. P I have taken into this side, and minus sign will be there as it is. PVF is this, PVI is this, correct? Now, PVF is this. So what we can write here, you see, we can easily take this RT outside. So minus of RT, in bracket we have final number of moles for gas minus final number of moles for initial number of moles of gaseous reactant. This we write it as delta N G RT. And that's why the work done is this, minus of delta Ng RT. Okay, now coming back to this point, and that is what we have substituted this thing over here, and the formula becomes this, because the initial formula is what? Del H is equals to del U plus P delta V. P delta V is nothing but delta Ng RT. Okay, now you see, if delta Ng is less than 0, means what? Work done is positive, and work done is positive means what? Work done on the system. Work done positive means what? Work done on the system. On the system, work done means what? Compression takes place. All these data you can easily retrieve from this. Okay. Now, when delta Ng is greater than 0, it means work done. If this is positive, means work done is what? Work done is negative. Work done negative means what? Work done by the system. By the system. By the system means what? Expansion. So whenever negative work we have, it means expansion takes place. Right? So if you have some example of reaction, if I write down, you see this. If I write down the first reaction, 3O2 gas gives you 2O3 gas. What is delta Ng for this reaction? Less than, what is the value of delta Ng? Or if I write down CaCO3 solid converts into CaO solid plus CO2 gas. Delta Ng. One more, if I write down N2 gas plus 3H2 gas gives you 2NH3 gas. Delta Ng. You see, for this one, delta Ng is what? Gaseous product minus gaseous reactant minus 1, it is negative. Gaseous product is 1, there is no reactant, right? So minus 0, so it is 1. Here we have 2 minus 3 plus 1 is equals to minus 2. Okay, so like this we can find out delta Ng and we'll get the idea of what? Idea of whether expansion takes place or compression takes place. Okay, whether expansion or compression takes place. Okay, so the next we have to understand is various process. Okay, and this one is again the most important thing in this chapter. Okay, what are the different types of process we have? What are the different types of process? Yes, various thermodynamic process. Isocodic, isothermal, adiabatic. Okay, so basically we know all these process, like most of you have this idea. Isothermal, temperature constant. Isobaric, pressure constant. Isocodic, isocodic, volume constant. Then we have adiabatic, no heat exchange, right? So del Q is equals to 0. Next one, what we have? Uh, cyclic process. Then we have reversible. And seventh one, we have irreversible process. Okay. Cyclic process, in cyclic process, del U is equals to 0 always. Right? Even whatever the state function we have, all change in 0. Because in cyclic process, we know the initial and final state are same. Right? From where you start, you comes finally at that position only, right? So this is a cyclic process we have, suppose. Right. We start from this point A, went to B, and then C, and then D, and finally at A. Right. We can have cyclic also. Right. Like this also we can have the process. Okay. So this is the cyclic process. Initial and final state are same. And I hope you know all this isothermal, isobaric, isochoric, and all. So I'm not discussing these things. Right. One thing is important for this cyclic process. You write down that one. Okay. See, whenever you have this kind of cyclic process in the question, right? With this arrow, you will understand that whether it is going into clockwise manner or anti-clockwise manner. Okay. So one thing you must keep in mind, sir, how is enthalpy zero in cyclic? See, enthalpy is what? Enthalpy is the state function, right? So it depends on initial and final state of the process. Suppose you are going from here to here. Enthalpy has nothing to do with what path you have chosen from going, like when you go from one state to another state. It it only depends on the initial position and the final position. That is it, right? So you see, at this point, suppose you are starting and finally you are coming over here only, right? So the enthalpy change is what? Initially the enthalpy we have at this point, and final enthalpy is what? At this point only. Initial and final enthalpy is same, that's why it is zero. Correct? So enthalpy change, whatever state function we have, if you write entropy also, usually, right? But there are many conditions in case of entropy, that's why we do not write here. But usually, as we talk about only state function, then entropy change will also be zero. If there is no mixing of gases and all, then whatever state function we'll have, the change in state function will be zero. Now, cyclic process, you see, if the process, because if the process is given, like here you see it is clockwise, right? So when clockwise process is there, then what we assume that work is always done by the system. Clockwise is work done by the system, which is always negative, the assumption we have. Anti-clockwise, if it is given, it is work done on the system. Work done on the system, right? So this gives you positive. This you must keep in mind. Okay. Now, if I give you one question here, right, and if you see this diagram on this, this is pressure and this is volume. Pressure is in, suppose, atm, and volume is in liter. Okay. Now we're starting from this point A, B, C, and D, and we are going like this and this. At this point, the pressure is suppose 10 atmospheric, and at this point, the pressure is 5 atmospheric. The volume here is suppose 4, and here is suppose we have 8 liter. You have to find out work done in this process, A to B, B to C, C to D, D to A. Tell me the answer. I'll give you 1 minute. You just solve this and tell me the answer. Okay, so all of you are getting minus 20, right? See, there are two methods to solve this, right? There are two methods to solve this one. Okay, first one, you see, for A to B, if the process is going from A to B, what is the work done for this WAB? If I write, that will be minus P del V, right? Minus P delta V. Now, since I have taken minus P delta V, so just you have to write whatever pressure we have initially. I'll not solve this, just I'll tell you this. 10 into final volume minus initial volume, 8 minus 4, right? Final volume minus initial volume, 8 minus 4. Work done for B to C will be what? 0. Work done from D to A will be 0 because both are constant volume process we have. So delta V is 0. Work done for C to D, if I write, that will be what? The pressure is 5 minus 5 into the final pressure is 4 and initial pressure is 8, which is 20. Yes. And what is this? It is minus 40. Total work done is what? All these you have to add, you will get minus 20. Okay. So now you see one thing also you can observe. A to B we are going. Means this is what? This is expansion we have. Volume is increasing. C to D, it is compression. Expansion means what? Work done by the system. Means work done must be negative here. That's why you see we are getting negative value here. Right? Compression means what? Work done on the system must be positive. You are getting positive value here. Like this, you can cross check. Okay. Now another way is what? Since you see the next method, which is the easier one, I think you all have done like this or what? Yes or no? You all have done like this only. Okay. You tell me one thing. Suppose if you have an axis y and x, and if I have to find out the area of any curve on this axis, how do we find out? We'll find out y into x, just we multiply the two axes that we have, right? Here also you see if you have to find out the work done of this, right? Then what you have to find out the area of this curve that you have, the graph that you have. Work done we know it is minus P delta V. So P into V, if you do, it gives you work done. Pressure into volume gives you work done, right? So this pressure into this volume axis, if you have pressure volume axis, then you can directly find out the area of this that gives you the what? Work done in this process. Now you see this difference is 4, right? This is 5 from here to here. And this difference is what? 4. So length into breadth is nothing but the area of this. So length into breadth is what? 5 into 4 gives you 20, right? So this gives you the magnitude actually. The area method gives you magnitude, right? But how do we get this sign? That is another question, right? And for that, what I told you, if clockwise is there, see the arrow I have given you, clockwise, it means it is clockwise. Clockwise means what? Work done by the system. Work done by the system means what? It is negative. So answer will be what? Minus 20. Did you get this? Right? Okay. So if you have pressure volume thing is given, then you can find out this easily directly by calculating the area. Okay, directly by calculating the area into this. Okay, now one more question in this we'll see. For cyclic process, I have given you del U, del H, del S, del G, right? Delta T, all these will be zero. All state function, change in state function will be zero, right? Now, if I ask you one question, because a graph related question they often ask in this particular chapter. So you have to, you have this graph. Okay, this is, let me draw the graph first. Suppose the graph we have this. This is pressure and this is temperature. Pressure temperature axis we have. Okay, this is A, B, and C. And the process is going like this. Now, this graph you have to convert in pressure and volume, right? And one more conversion we'll see, that is volume and temperature. Because sometimes, what happens, if you have pressure volume graph, then you can easily find out the area and you will give the, what is the time now? Okay. We'll do this after this only. I'll give you the break. Okay, because after this we have to start reversible, irreversible process. Okay, so that will take some time. Yeah. Give me 5 minutes. Okay, 5-10 minutes you give me. I'll give you the break. Okay. So you see why this is important, because sometimes if they want to twist the question, suppose you have pressure volume graph, then you can easily find out the work done, right? And we have to mainly deal with work done in this chapter, right? So pressure volume graph, you can find out the area and you will have the work done. But sometimes if they really want to twist the question, they will not give you pressure volume graph, they'll give you pressure temperature graph or volume temperature graph. Okay, then how do we convert this into this? Okay, so now how do we approach this particular uh, graph, that we have to understand. First of all, you try to identify what all process we have here. You see, I have given this line from here to here. It means this line is passing through the origin. And when it passing through the origin, it means for process A to B, volume is constant. Yes or no? Tell me. A to B, yes, volume is constant. What about B to C? What about B to C? Isothermal process, constant temperature. And C to A is what? Isobaric process, constant pressure. Now we have to draw the graph in such a way that all these conditions are satisfied. Okay. So A to B is what? A to B is volume constant. So volume we have here, right? So A to B we cannot go like this, right? We can go like this, or from top to bottom or bottom to top. So obviously we have one line like this. Yes. Now in this point, this can be A also and this can be A also. That we are not sure right now. Right? This can be A also, this can be A also. When I write this A, it means the process is going in this direction. When I write this A, it means the process is coming in this direction. Correct? Now, B to C is what? B to C is isothermal process. So for PV graph, isothermal process, we know the graph goes like this. Okay. For Boyle's law, we must have done, no? The graph of PV is like this in Boyle's law. Constant temperature. Right? So constant temperature graph is this. Now C2A graph is isobaric. Isobaric means pressure constant. So pressure constant graph will be like this, right? Now you see A to B we are going, A to B, we have constant volume but pressure is increasing, right? Like I said, this point can be A or this point also can be A. So which point will be A, that we are going to decide now, right? You see from A to B the pressure is increasing at constant volume. So if you write this A and this B, then the pressure will decrease, correct? So we have to write A over here, B over here, and third point is C. If I put the arrow, then A to B, pressure, you see the pressure is also increasing, volume is constant, right? B to C, the pressure is decreasing, you see pressure is decreasing and volume is constant. C to A, constant pressure, you see C to A we have constant pressure. This is the graph we have, of pressure volume graph. Did you understand this? Okay, now if we have to convert this into pressure temperature graph, now you see if PV is equals to nRT, if you apply nRT, volume and temperature we have to think, means pressure is constant. So for constant pressure, the line must passes through what? Origin, right? Constant pressure graph, what we have? C to A, right? So C to A must pass through origin like this, suppose. So I'll give this is C to A, right? Now which point is C, which point is A, that we have to identify again, right? C to A, if you are going, you see the temperature is decreasing, right? So obviously in this process temperature must decrease, right? So you must have to write down C over here and A over here, correct? Now AB graph is what? Constant volume. So constant volume, obviously AB graph will go like this, parallel to the y-axis, this perpendicular to this y-axis exactly, right? And C to B, B to C is isothermal. So you'll see this B to C is isothermal. This is B point. Okay. So if I write down arrow here, B to C, you see constant temperature but volume is increasing. B to C, constant temperature, pressure is decreasing, means volume will increase, right? C to A, C to A, you see constant pressure, temperature is decreasing. C to A, constant pressure, temperature is also decreasing, right? A to B, constant volume but temperature is increasing, right? So A to B, you see constant volume but temperature is increasing. This is what the graph of DT we have. Understood? So like this, if you have any graph given, whether it is pressure temperature graph you have or volume temperature graph we have, we can easily convert this into pressure volume graph and then we can solve the question. Okay, so we'll take a break. It's 6:15 almost. Okay, at what time will you start? You tell me. 6:30. Correct. We'll start at 6:30 sharp. Okay. Make sure you are present. Okay, don't go anywhere because we have to discuss reversible, irreversible process. That is very important. Okay, 6:30 will start, 6:30 sharp. Yeah, hello. Can we start? Who are there? Hello. Who are there? Okay. So the next thing we are going to discuss is reversible and irreversible process. Okay. Reversible and irreversible process. See, before discussing this reversible and irreversible process, one thing I want to ask, you must have done the derivation of um, isothermal reversible process, right? Isothermal reversible process, and then in that we have done the derivation, that is dw is equals to minus integral of p dv, right? v1 to v2. And then what we have done into this, we have taken this pressure outside dv, and then we derived the relation, if you remember. Yes, we have done this derivation, right? Did we take this pressure outside or not? Oh, it is reversible, no? So we haven't done this, right? Okay, let it be this one. We have two actually way here. Either we can take this pressure out, or we can let it be this pressure inside, and we can substitute this as nRT by v dv, and then we can integrate. Yes. So since it is reversible, right? So we have done by this way, not by this way. Okay, means in this thing the pressure is not constant. Yes, that is what you have to understand here. If you try to recall, you have done this derivation, and we have done in this dw is equals to minus p delta v, and since this reversible process, we can't take this pressure outside the integral sign, and then we substitute this as nRT by v, and then we have done the derivation into it, right? So now the point here, some of you must have this doubt, that why we not take this pressure outside, because the expansion or whatever it is takes place against the constant external pressure, right? So for that you have to understand reversible and irreversible process first. Okay, generally what happens, reversible process, we do that, we say that these are the process which takes place in both direction, forward also and backward direction, right? It is bidirectional process. Okay, any state we can anytime we can convert or we can reverse the process itself. Okay, and we can go to the initial position, right? That is what the definition generally given, right? But that won't help you solving the question. Okay, so first of all you have to understand this reversible and irreversible process, and for that I am going to draw two piston cylinder system here, and with this I am trying to explain what is reversible and what is irreversible process. This is the one system we have, and this is the another one. Okay, suppose the first one we have a movable piston, right? And this piston is somewhere here. We have some gas over here which is not actually required, but I told you this. Okay, and this gas will apply some pressure on the piston, and this piston will also, the external pressure will also apply some pressure on the gas. And wherever we have this equilibrium, then the piston will be static. Okay, so what happens here? Suppose if I put some particle here, suppose if I put some sand in a bag, like I take some bag, okay, and in the bag I put some sand, and then I place this entire bag here on this piston, right? Like this bag filled with sand over here, right? Now this, because of this bag will have some pressure downward, and then the piston and the gaseous pressure, wherever it is equal, there the piston will be static, right? Now if you want to remove this sand bag from here, right, we can do this in two different ways. What are those? You see, all of a sudden if I remove the sand bag completely, right, then piston all of a sudden will go up, and then wherever the atmospheric pressure and the pressure of the gas will be equal, there the piston will stop, right? Further it won't go up. Okay, another way is what, we can remove the sand slightly from this bag, right? Little bit, like we remove the sand little bit, then again the piston will go up, equilibrium will maintain. Again we'll remove the sand, again the piston will go up, equilibrium maintain, and this process also takes place. Okay, suppose this is state 1 we have, and this is the state 2, right? So from state 1 to state 2, if you have to go, right, this thing or this like the position, this final position we can achieve in two ways. One is what, all of a sudden you remove the sandbag, or second way is what, you keep on removing the sand particles slightly, like in a given time interval, right? So you remove a sand particle, it goes up, static. Again you remove, again it goes up, and it goes till here when all the when the bag you'll remove completely, right? So two process I have discussed, two way I have discussed. When you remove this sandbag completely, what happens? This piston all of a sudden will go up, right? So this process is what? This process is very fast process, right? And this process we call it as irreversible process. Irreversible process, right? The second way that I explained you, that you keep on removing the sand particles slowly, and then you again achieve the final state. Okay, that process is reversible process. Reversible process. So now you think on it a little bit. Okay, in reversible process, what happens? Continuously, we are removing the sand particles, right? Means the pressure that is exerted by the bag is continuously changing, right? That's why in this method, isothermal reversible process, what we say that this pressure is the function of volume here, right? And we cannot take this outside, so we substitute this pressure in terms of volume, and then we integrate. Understood? Any doubt till here? Any doubt? Who all are there? Tell me. Hello. Okay, yeah, I could not. Okay, I could not see the messages. That's why I stopped. Okay, anyways, so you see, basically, there are few points you have to keep in mind here, right? A reversible process, like I said, okay, it is a step-wise process. Okay, in irreversible process, what happens? All of a sudden, piston goes up, right? In irreversible process. So actually, this expansion or compression, whatever it takes place against a constant external pressure. Okay, so there are few points in this you write down which is important. Okay, this is important with respect to your board exam also. Okay, they ask question on this. Okay, okay, so write down in irreversible process first. It is a unidirectional process. It is a unidirectional process, and it cannot be reversed, and it cannot be reversed along the same path easily. It cannot be reversed along the same path easily. Okay. The next one we have, it has finite number of steps. It has finite number of steps. Okay. It is a fast process. Fast process. And the system is at thermodynamic equilibrium at only initial and final step. initial and final step. It takes place against constant external pressure. Constant external pressure, right? Now, if this equilibrium we have at initial and final step only, so we can apply this ideal gas law, PV is equals to nRT, at initial and final step only, right? At initial and final step only. Now, the next, for reversible process, you write down reversible process. That's why one more thing, if I tell you here, any work done calculation, right? dW is equals to minus P dV, V1 to V2 if you have to do in irreversible process, then we can simply take this pressure outside, because it says simply that it takes place against the constant external pressure. So we can take this minus P outside V1 to V2 dV, which finally gives us minus P delta V as the work done in irreversible process. But this pressure we cannot take out in case of reversible process. Why external pressure is not constant? Because as I said, that we are continuously removing the sand particles from the bag, right? From the bag. So if you remove sand particles continuously, so the external pressure is continuously changing. As the pressure is decreasing, this piston is slowly going up, right, to the final state, right? Since the piston is slowly going up, that's why we call it as a very slow process, right? Which takes place against variable external pressure we have actually, okay? And since it is slowly going up to the final step, so it contains infinite number of steps. Okay, infinite number of steps. This is on one point. Each step will be in thermodynamic equilibrium. Each step is in equilibrium. Okay, so here we can apply this PV is equals to nRT at every step basically. Okay, P external pressure is not constant, okay, and it is a very slow process. And since suppose you are removing one sand particle from here and the piston slightly goes up, again you put the same sand particle into the bag, the initial position will be restored, piston again comes down. Okay, so in this what we say, that we can reverse the process at any time, and the original position will be restored. Original position will be restored. Okay, now if I try to make you understand these two things with the help of graph, right, with the help of graph, if I try to make you understand, you see we are drawing this only one graph. I'll make you understand in this. Suppose we have pressure volume graph, right? This is pressure volume. I'll try to make you understand isothermal irreversible process and isothermal reversible process. Okay, isothermal irreversible and isothermal reversible process. Since it is an isothermal process, so the pressure volume graph will always be like this. Okay, suppose initially, like I take this piston cylinder system, right? Initially the piston is here, right? This is state 1, right? And we have the bag actually, okay, sand particles, right? So here we'll have some pressure because this sand part, the pressure will be obviously more. So suppose initial pressure is somewhere here, right? It is the pressure we have P1. And when, since irreversible we are talking about, this bag you remove all of a sudden and the piston goes up and we get the equilibrium here at some position here. So this is the final position, initial position, this is the final position. So there will be expansion, right? So volume increases. So initial pressure, suppose we have here, and all of a sudden when you remove the bag, the process goes like this since it is isothermal. And this is what the pressure P2, right? Here we have the pressure P2, right? So this is what, this is one step. From here, you remove this bag, all of a sudden this comes over here, right? And the volume increases. You see the initial volume we have here, V1, and the final volume is V2, right? Now the same thing, the same state we can also achieve reversibly also. And what happens in reversible process? Now you pay attention here, right? Suppose if you are removing the sand particles, so pressure slightly decreases, right? So first step you see, if the pressure slightly decreases, suppose the pressure comes over here, right? This is the pressure we have, right? It is P1, P2. Suppose if this is, if I write um, P dash. So we remove the sand particles slightly, pressure decreases, and in this course, expansion takes place a bit. So this is the expansion we have. So according to this also we'll have some volume here. Again you remove sand particles, right? Again from here, the pressure decreases, right? And in this course, expansion takes place. This is, suppose we have P double dash. Again you decrease pressure, it comes down here, right? And again, in this course, some expansion takes place like this. And this pressure is, suppose we have P dash. Finally, if the pressure becomes P2, the expansion will be like this. Okay. So you see, in irreversible, this, the blue one we have here is what? This blue one is the expansion we have for isothermal irreversible process, and the red one is the expansion we have isothermal reversible process, right? You see, the number of steps involved in isothermal irreversible process is equals to one single step from here to here it comes, right? Number of steps here is 1, 2, 3, 4 steps we have basically. Okay. So one more thing we can conclude from here, as the number of steps as the number of steps increases, then the process has tendency to behave more like reversible process. Any doubt you have in this, you can ask me now. Okay, so if you increase the number of steps on the basis of this also, they can ask you some question. Okay, you see, each step will be in equilibrium in reversible process, right? But this kind of equilibrium only exists in initial and final step in case of isothermal process, isothermal irreversible process, right? So that is why you see this expansion takes place from here to here. This expansion takes place against this external pressure. This expansion takes place against this external pressure. This expansion takes place against this external pressure. Like this, you see, in case of reversible process, the external pressure is continuously changing, right? That's why while we do the derivation of isothermal reversible process, we cannot keep this pressure term outside the integral sign, and then we substitute this pressure in terms of volume with the help of ideal gas equation. PV is equals to nRT by V dV, and then we integrate that and we'll get the expression. Okay, did you say in reversible reaction there are infinite steps, but doesn't it have finite steps in the graph? See the graph. See, the point is, we decrease. You remember one thing, in isothermal reversible process, we decrease the pressure by very small amount, dP. This graph I made for you to understand. Actually, if you decrease, suppose pressure we have 10 atmospheric initially, right? So from 10, if you decrease the pressure by 0.00001, then also some expansion we have here. Again, you decrease further pressure 0.00001. Then also some expansion we have here. That's why we are saying it has infinite number of steps possible. What I said, you have a sandbag here. You remove one particle from this, one sand particle. What is the mass of that? Negligible. Okay, but that also leads to the some expansion into this. Okay, that's why we say infinite number of steps. Okay, so if you have this concept clear, they ask this question in board exam also, the difference of irreversible and reversible process. So everything 4 5 steps you can write down. If you draw this graph, you will get full marks. Okay, there's nothing more than this, and that is how you can understand wherever we have irreversible process, take pressure constant, P del V will give you the work done. But in case of reversible, this pressure is a function of volume. Accordingly, you have to solve. Okay. So I hope you all have done that derivation of isothermal reversible process and all. So I'm not going to derive that one. Okay. That will get 2.303 nRT log of V2 by V1. Like that, we'll get some expression. Yes or no? Okay, so that derivation I am skipping. Okay, that I am not doing. You can go through it. It is given in the book. We don't have that much time. Okay, so now you see the graph of isothermal and adiabatic process. Okay, so if I draw the PV graph here for isothermal process, it is like this, and the same kind of graph we have for adiabatic process also. PV graph. This is for suppose isothermal, and this is adiabatic. Okay, so it is important to identify the graph. Okay, for this one, you see, since it is isothermal, so we can always write PV is equals to some constant K, and for adiabatic we have PV to the power gamma is equals to constant. Okay, this also we can derive. Okay, again derivation we are not doing, we are skipping that. Okay, only concept we are discussing. Okay, derivation you can go through in the book. If you have doubt, you can ask me. Okay, I'll explain that. Okay, now you see, if I calculate the slope of this graph, right, the slope will be what? Any graph, if you have y or x, then slope will write what? Dy by dx. Okay. Similarly, we have PV graph, so slope will be dp by dv. Okay. So dp by dv, if I calculate from this, that will be minus k by v square. Yes or no? Tell me. And k we can write as PV. So finally, we'll get the graph as P by V minus P by V. The slope in isothermal process is minus P by V. Yes or no? Correct. Similarly, if I calculate the slope in adiabatic process, dP by dV, that will be equals to minus of k into gamma, right, divided by V to the power gamma plus 1. Right. Further, if you simplify this, we can write what? Minus gamma into k by v into 1 by v to the power gamma, and k by v from this expression k by v, sorry, we have this constant k will write here. So 1 by v to the power gamma is equals to what we have? P by k is equals to P by k. If I substitute this here, we'll get what? Minus gamma into k by v into p by k. K and k gets cancelled, and we get gamma into minus of p by v. Okay, so this minus of p by v is what? It is the slope in isothermal process. So when I equate all these p minus v from these two expressions, we'll get slope in adiabatic process is equals to gamma times slope gamma times slope in isothermal process. Okay, is it clear? Is it clear? Slope in adiabatic process is equals to gamma times slope in isothermal process. Now, if you see for monoatomic gamma value, is 1.66. For diatomic gamma value is 1.4. For polyatomic gamma value is 1.33. Whatever the value we have, gamma is always greater than 1. Right? Since gamma is always greater than 1, so work done, sorry, for that's why we can say the slope for adiabatic process is always greater than the slope for isothermal process. Is it clear? Adiabatic process. So if you see the graph, you can understand what slope we have, right? But what graph we have actually. Okay. So if I again, can I rub this off? Okay. Now you see, if you have two graph given, right? This is very important, right? Now if you have two graph given, you have to identify which one is for isothermal and which one is for adiabatic. The first case we are taking, that is expansion. Only small graph we have. Expansion means what? Work done by the system. Okay. Here you see we have two graph, right? One graph I am giving you. Let me draw the axis first. One graph I am giving you when the final pressure is same, right? This is suppose the initial thing we have, this graph, and Okay, you see the final pressure in this graph is same. Okay, this is the initial pressure Pi, and this is final pressure Pf. Since it is expansion, so it is coming like this, it is going like this. Okay, this is the one graph we have, and this is the another graph. You have to identify which graph is isothermal and which graph is adiabatic. Okay, this when final pressure is same, another one when final volume is same, like this. When final volume is, this is Vf, this is Vi, and this is pressure axis, volume axis, and volume axis. Can you draw the isothermal and adiabatic graph together in the same? Ah, that is what we are doing here. You see, we can. See, don't mix this thing with the. You must be thinking about whether a process can be isothermal and adiabatic both at the same time. Okay, that is not the concern. The concern is if you have any process which is isothermal, so we can draw the graph. Same we can draw if the process is adiabatic also, right? That is what it has nothing to do with the process, whether the process can be isothermal or adiabatic at the same time. That is not the meaning. We are just trying the two graph. We are trying to compare the two graph here. Okay, adiabatic and isothermal. Okay, so you see in this, if the suppose if the graph, if the process is isothermal, right? Isothermal process means what happens? The temperature must be constant, right? Adiabatic process means what happens? That the heat exchange is zero. So since the expansion is taking place, so system is doing work done by the system we have. So in case of adiabatic process, what happens? System is doing work at the cost of its own internal energy, since it cannot take energy from outside while since the process is adiabatic. Is it clear? So adiabatic process, you write down, system is doing work at the cost of its own internal energy. System is doing work at the cost of its internal energy, capital U, right? So now when the system internal energy is decreasing, it means what? Its final temperature is also decreasing, because internal energy is a function of temperature. Right. So when the internal energy is less, obviously its temperature is also less. Okay. And when the temperature is less, right, final pressure is constant we have for both the process. So from PV is equals to nRT, we can say its volume is also less. Yes or no? Tell me. Correct. Did you get this? Okay. So now you see this graph. Now it is very clear. What we like conclude from this, in adiabatic process, final temperature will be lesser, and hence final volume is also lesser, correct? So where we have less volume, the lower graph, right? This is the lesser volume we have. It means the lower graph is for adiabatic process, and this graph is for isothermal process. Is it clear? See, what did I say? That we are discussing about this two graph, isothermal or adiabatic. So let's talk about adiabatic process first. Okay. See, since expansion is there, volume is increasing, and we know expansion, whenever it is there, work done by the system we have. Okay. Work done by the system we have. Correct. Means when the system is doing work, and since the process is adiabatic, so it cannot take energy from outside, right? So it has to do work, system has to do work at the cost of its own internal energy, right? And hence what we say that its internal energy decreases. When internal energy decreases, it means temperature is also decreases, right? And when temperature decreases, and temperature and volume are directly proportional. Why? We see because the final pressure is same. This is the condition we have for final pressure. Two graph we have right down here. When the final pressure is same, when the final volume is same, right? When PF is same here, these two condition we are taking, and when VF is same here, you'll get graph like this only, correct? So when the final pressure is same, so we know the final temperature is directly proportional to final volume, right? So when final temperature is decreasing, so final volume will also decrease, correct? So that's why both of these graphs, which one will have the lesser volume, that will be adiabatic, and higher volume will be isothermal. Clear? Understood? Okay, now the same logic you see you can apply when the final volume is same, right? Final again adiabatic process, the work is done at the cost of its internal energy. So internal energy decreases, so temperature decreases. Temperature decreases since final volume is same here, so we can talk about final pressure here. When internal energy decreases, so final pressure will decrease. So final pressure we have here for this graph. So this graph is again adiabatic, and the upper graph is isothermal. Like this, we can identify the graph. How many of you understood this? Quickly, we have 10-15 minutes. We have to do some questions on this. Okay, this graph things are important. Yes. Okay. Now this thing will just get reversed in the case of compression. Okay. What you have to keep in mind whenever you have expansion, the lower graph is adiabatic and the upper graph is isothermal. But in case of compression, when final pressure is same and final volume is same, then always we have the lower graph is isothermal and upper graph is adiabatic. Just you write down here the same thing. In case of compression, in case of compression, you can think on this, okay? Lower graph is isothermal and is upper graph is adiabatic. This you must remember, okay? Adiabatic and isothermal graph. Okay, you can think on this like we have explained this. You can think simply on this. If do it at home, okay? If you have doubt, you can ask me. I'll explain this in the next class. Okay, how it is lower and upper one. Okay. Now you see one question I am giving you. Actually, we'll solve two questions. One question I am giving you, and the another one which they have asked in JEE exam. Okay, that we'll discuss onto this graph thing. Okay. So suppose we have this graph given, right? Pressure and volume graph we have. Three different graphs. One, two, and then three, right? This is the first graph we have, second graph we have, and this is the third. Okay. Now you have to answer that which of these graph represents monoatomic gas or diatomic gas and polyatomic. And this is the expansion we have here. Okay, expansion graph is given. You have to identify which one is monoatomic gas, which one is diatomic gas, and which one is polyatomic gas. Mono is 3, 2 is di, okay. You see, first of all, you tell me one thing. Whether this, since it is a PV graph, right? Whether it is adiabatic graph or isothermal graph. First, you tell me that. What graph it is? It is adiabatic graph or isothermal. What graph we have it is? Adiabatic or isothermal? Where is Shweta? Shweta, tell me the answer. Why it is adiabatic, Aditi? Sanjana, what is the answer? Pratik, where is Pratik? Purvik? Okay, you see, if you see the isothermal graph never intersects. You must have seen the graph isothermal like this. Okay, so this isothermal graph never intersects. Write down. Okay, that is what I'm telling you, Sanjana. Isothermal graph you must have seen at different temperature, PV graph. They never intersects. They are parallel like this. Okay, so that's why this graph is what? This graph is adiabatic graph here, which is given since they are intersecting at one point. Okay, right? So now the first thing we have to identify in this whether this graph is isothermal or adiabatic. Since they are intersecting, so they are adiabatic graph. Now you see the graph that I have drawn in the last this thing just before this. That is, one is adiabatic, another one is isothermal, right? What is the case we have here? It is expansion. And expansion, we know the lower graph is what? The lower graph is adiabatic and the upper graph is isothermal. For isothermal, what condition we have? PV is equals to constant. Adiabatic, the condition we have what? PV to the power gamma is equals to constant. Okay. So can we say one thing? Because what is the power of V over here we have? Here you see the power of V we have 1 in case of isothermal. In case of adiabatic, the power of V is gamma, which is more than 1. Yes or no? Correct. So can we say one thing? As the power of V increases, right? When the power of V increases, the graph starts shifting down, right? It is shifting towards this side. Okay, it is coming down. Yes or no? Can we say this? As the power of V increases, the graph shifted this side, okay, towards the down, right? Downside, downwards, it is shifting. Correct? It means more value of gamma, more shifting of graph will be there downwards, right? And we know the value of gamma is maximum for which one we have? Value of gamma is maximum for monoatomic. Then we have what? Diatomic. And then we have polyatomic. So maximum value of gamma, it means the graph will be downwards maximum. So this third represents monoatomic gas, second represents diatomic gas, and the first represents polyatomic gas. Is it clear? All of you understood this? Okay. Now you see one question which was asked in JEE 2012. Okay, it is a multiple correct. Okay, JEE 2012 question we have. PV graph is given. Let me draw the graph. Pressure volume graph is given. Okay, here it is given, it is P1, V1 and T1 at this point. At this point, it is P2, V2, T2, and at this point, it is P3, V3 and T3. Okay, expansion graph we have. Okay, expansion. So which one is isothermal and which one is adiabatic? Which one is isothermal and which one is adiabatic? The answer is clear, right? The upper one is what? Isothermal, and the lower one is what? Adiabatic. Right? But this is not the question, Purvik. Aditi. The question is something else. It is given in the question that the upper one is isothermal and lower one is adiabatic. It is given in the question. Okay. So the question is what? First option we have, you have to tell T1 is equals to T2. Possible or not means you have to tell me the answer. More than one correct we have into this. Second option we have T3 is greater than T1. Third option we have work done in isothermal process is greater than work done in adiabatic process. Okay. Fourth one, del U for isothermal process is greater than del U for adiabatic process. Who said both are adiabatic? The upper one is isothermal. Same here. The upper one is isothermal and the lower one is adiabatic. See, Sai, you don't confuse with this that the graph is getting graph is intersecting at one point. See, it is not like we are not talking about the one same process which is isothermal and adiabatic both. The same question that Shweta probably asked that time. Okay. The thing is, we are just giving you two graphs. One is isothermal and other one is adiabatic. Okay, one is isothermal and other one is adiabatic. The upper one is isothermal, the lower one is adiabatic. Okay. And on the base of this graph, you have to tell me which all options are correct. Aditi, only one. Which temperature is different? That is what? That is what? You have to answer. Saimir, you have to answer that only. If it is isothermal process, then the temperature must not be different. All are saying 1 and 3. One is very clear, right? Because the temperature, because the process is isothermal, so obviously T1 is equals to T2 is correct, no? If the process is isothermal, then T1 is equals to T2 is obviously correct. Right? Do we have T3 greater than T1 possible? No, because what I said, because this process is adiabatic, and this expansion takes place at the cost of its internal energy. So that's what I have given you there, that the temperature decreases in this process. So obviously this T3 should be less than T1. Okay, so this answer is not correct. The correct answer of this is what? T3 should be less than T1. This one is correct. Yes. What about isothermal and adiabatic? Third one is correct or not? Third one is also correct, because you see, if you have to find out the work done in isothermal and adiabatic process, what you'll see? You'll see the area under curve, right? So area under curve in case of isothermal process is this, right? Area under curve in case of adiabatic process is only this, right? So obviously the area under curve in case of isothermal process is more. So obviously the work done in case of isothermal process is more than to that of adiabatic process. Okay. But since you see one more thing here, you just keep in mind, work done by the system we have, so that must be negative. Okay. So if you take this, the magnitude of work done in isothermal process is more than the magnitude of work done in adiabatic process. Right, this mod is not given in the option, but we have to think like this. If you include minus sign here, then the sign will reverse. Okay, now you come to this fourth option, right? You see, change in internal energy in case of isothermal process is always zero, since the temperature is constant, because internal energy is a function of temperature itself, right? Change in internal energy in case of isothermal process is always zero, but change in internal energy in case of adiabatic process, when expansion is taking place, in this case, right? Expansion again means what? Work done by the system, right? Work done by the system means what? Internal energy decreases, since the process is adiabatic. System cannot take energy from outside, it has to do work at the cost of its own energy, right? That's why the internal energy decreases, and when the internal energy decreases, the change in internal energy in adiabatic process is always less than zero. Correct, Vaishnavi, right? So obviously the isothermal process will have larger internal energy than adiabatic process. Okay, so if I write down mod here, right, then it is correct. Third option I'm talking about. Okay, but in the question, if they didn't give you this mod here, then this option will be wrong. You must take care of one thing, because what I said, graph only gives you magnitude. That one question we have discussed now on by the system or clockwise, anti-clockwise. If you calculate work done by the, like, the logic of this area under this curve, that gives you only magnitude, right? So magnitude of work done in case of isothermal process is more than adiabatic process. So this option is only true when you write down magnitude here, right? If you remove this mod, then this option will be wrong in that case. Is it clear? Third option, is it clear? Yeah, so with magnitude, the correct answer will be 1, 3, and 4. But if magnitude you remove, correct answer will be 1 and 4. Okay. So like this, you can compare and you can do this. Okay. So like we are done for today. Okay. We'll wind up the class here only. We are left with only that gives free energy, some concept we have there, and then entropy thing. Okay, so that we'll discuss in another class. Okay, since this was the extra class we have, so we'll take one more and then we'll do that also. Okay, second law of thermodynamics we are left with. See, I tell you one thing, this chapter is quite big. Okay, and all these, you see, every single concept, if you have to understand, you have to solve a lot of question and you have to think on this. Okay, one more section of this chapter we have, that is thermochemistry, that Hess's law and all, enthalpy and all, right? So that also we'll have questions from that also. That portion is also important for JE point of view. Okay, so this chapter is quite big. You are going to have one question from this particular chapter. Okay, so we cannot skip anything. Okay, you must have to be, clear with your concept in this. Okay, so the thing that is left in this thing is, in this chapter, is enthalpy. Enthalpy we have done, gives free energy and entropy. Okay, and then some physical significance of that also. Okay, so we'll probably finish this in next class. Okay, when we'll take that class, we'll let you know. Okay, so like my suggestion is, just go through with the previous year questions. Okay, you will see that many questions, we many things we haven't discussed today, we could not discuss today. Okay, but then we'll discuss that later on. But what all things are there related to first law and this work done in various process, those questions you can go through. Graph related questions you must do. Okay, so we'll see this in the next class again. Okay, thank you. Any doubt?